All right, that's better. Now I'm much louder. So my name is Greg Bryan. I'm faculty at Columbia and group leader here at the CCA and co-director of the Kavli Summer Program. My other co-director here, Rachel Somerville, and together we'd like to welcome you to this program. So we're going to say a few words, but before we get into that, we have a short video outlining the operation of the theater to show you.
Hello, and welcome to the Gerald D. Fischbach Auditorium, where your comfort is our #1 priority. Contoured ergonomic seats are equipped with an AC outlet and stowaway tray table that's just the right size for your laptop or electronic device. This state-of-the-art auditorium boasts a simple-to-use voice lift microphone system. When asking a question, push the speaker button on the chair directly in front of you. Lean forward and speak in a clear voice into the microphone. Watch those elbows, or you may turn on the speaker by mistake. When you're finished, push the speaker button again to turn off the microphone. Remember, food and beverages are never allowed in the auditorium. And that includes bottled water. In case of emergency, there are 4 exit doors. Please take a moment to locate the nearest door to you, keeping in mind that it may be behind you. Follow directions as you vacate the auditorium and depart in an orderly manner. Once on the promenade, use one of the 2 emergency exits to leave the building. The first exit is to the left of the restrooms. The second is next to the elevator. And please, when you're leaving the auditorium, never run. Thank you for joining us. Now relax and enjoy the program.
All right, now that you know how to use the auditorium. So I'd like to start us off with a few words of introduction about the Kavli program itself from Pascal Giroux.
So, welcome everybody to the 2018 Summer Program in Astrophysics. I'm the founding director of the program, and I wanted to spend a few minutes to give you a little bit of a history of the program so you understand better our vision for its future. The history is, I need to use this. The program is a spin-off of a really well-known program in applied mathematics and fluid dynamics called the Geophysical Fluid Dynamics Summer Program that is hosted every year on Cape Cod at the Woods Hole Oceanographic Institution. That program was founded in the early 60s by a number of faculty with interdisciplinary interests, some in physical oceanography, like George Veronis, Willem Malkus, Melvin Stern, and Henry Stommel, some in applied mathematics, like Joe Keller and Lou Howard over there on the turning table, and one astrophysicist, Edward Spiegel from Columbia. The program has been running since the 60s and trains 10 fellows every summer, so you can do the math, and has effectively trained 600 graduate students since then. Many of these graduate students are now faculty members at top research institutions worldwide, and some of them have actually been awarded top honors such as memberships in the National Academy of Science or Fellows of the Royal Society in the UK. The 60th program started last week and is going to go on for the rest of the summer as it has for the last 60 years. The GFD is very interdisciplinary in nature, and this here is a picture from the 1963 program, and some of these people you might actually recognize in this audience. In here, there's Alar Tumray. There are Ed Spiegel somewhere, can't see him. Ed Spiegel, Bob Kreishnan, who is a turbulence theorist, Don Osterbrook. So all of these people came to this program in fluid dynamics and applied mathematics.
Who's that guy lying down?
The guy lying down is Melvin Stern. He's a very famous physical oceanographer. So in the last 6 years, the program has essentially had the same format. After 2 weeks of research, the faculty stick around and advise the 10 fellows through research projects, and these projects usually get published within the next year. This picture here is from the 1999 program, and this is where everything began. This is me right there, sitting on the porch with everybody else. Many of the people who were there, the founding fathers of the program, are still around, George and Joe and Lou over there. And the reason I mention this is this program literally changed my life and launched me on the career, on my path to where I am now. In this program, for instance, I got to, I lost all my notes. Somehow they all disappeared. Oh well. Oh, here we go. So the project that I did as a fellow of the program was quite different from what I did during my PhD. And this is essentially that project that got me the fellowship, the postdoctoral fellowship that I got after I graduated. I also had the chance, through the fact that this is a very long summer, I had the chance to chat with Lou Howard and George Veronis, for instance, about research projects, and they wrote me the letters of recommendations I needed to get the faculty position I ultimately got. And the community that we built together that year and over the following years as I came back to the program is basically my family, my scientific family. They're friends, they're people I can turn to ask questions and to get ideas for new research projects. So now I come back to the program as a faculty mentor, and I advise some of the fellows of these years. And these are the top graduate students in the world, and it's always an amazing pleasure to work with them. So ultimately, this program was so fundamental to who I am today that I really wanted to share this benefit with the astrophysical community. And in 2009, I applied for an NSF Career Award to launch the same thing in astrophysics. It was initially called the International Summer Institute for Modeling in Astrophysics and was launched in 2010 in Santa Cruz. You could see it was very different from the settings we are in today. And every year the program grew in size. There are differences between our program and the GFD. It's shorter, it's only 6 weeks instead of 10. And the program tends to be much more thematically focused. As you can see this year, it's a very thematically focused on the computational astrophysics of galaxy formation. Beijing 2011, star and planet formation. Toronto 2014, gravitational dynamics. And it should be quite obvious, there's another big difference with the GFD program is that we travel around the world. We don't stay in one place. And so this year, we are in New York. In 2016, we reached out to the Kavli Foundation and asked them if they would sponsor the program, and they were very enthusiastic about it, and we're so grateful for their support. Thanks to that, we are now able to offer the program every year. In 2016, we were in Santa Cruz, in 2017 in Copenhagen, and finally this year in New York for this program. So just a few words about the Kavli Foundation itself, for those of you who don't know. It was founded in 2000 by Fred Kavli, and the Kavli Foundation is dedicated to the advancement of science for the benefit of humanity, promoting public understanding of scientific research and supporting scientists and their work. It supports 4 themes in astrophysics, neuroscience, nanoscience, and theoretical physics. And there are 6 of the 16 Kavli institutes that are dedicated to astrophysical topics. They also sponsor the Kavli Prize that awards the top researchers in the field in these 4 fields every year. And since 2016, it also sponsors our program. So together with our growth, we decided to write a charter to actually state the goals of the program and its long-term vision. So the Kavli program fosters excellence in both research and education. And I think you will see over the next few weeks how this actually plays out. It's the combination of the long-term research workshop together with a graduate training program that really gives it a new dimension compared to everything else you will have experienced so far. The students get a really unique educational experience, and the faculty will get a really unique research experience. The participating senior scientists are well-caliber researchers in their field, And they're dedicated. They've all come here to train new graduate students and postdocs to get the best research out of you. And the students and postdocs have all been selected through letters of recommendations, through many, many applicants from all over the world. You've been selected because of your outstanding promise. So this is a really unique selection of people sitting in this room today. The program also fosters innovation. You will see through the projects that these are really catalysts for new research. And I hope that you will take the time to really select the project that is the best for you. The program encourages participants to think outside the box and provides every day the intellectual stimulus for emerging fundamental and innovative idea. And you will see all throughout this week and in the next weeks of the program, there are many chances for informal discussions to really learn about each other's science. I hope you're not going to stick around in your office for too long every day. Actually, go out there and talk to each other. In particular, students, you have the best field in the world right now at the CCA, working in your discipline, so make the best out of it while everybody's around. And for the first week especially, really do take the time to talk about these projects to make sure you have the best project for you. And finally, the program fosters community. And this is probably the biggest pillar of these three, even though it might not seem so at first. Our main goal is to create an international community of like-minded scientists. And at the beginning, it will seem like a professional community, but I hope that by the end of the program, it'll also be a social community across disciplines, age groups, and across continents. In particular, we are making a point of inviting scientists at all stages of their career. And I encourage you students to really talk to the postdocs about their career experience. And I encourage you postdocs to talk to the faculty about your career experience. And finally, I would really like to encourage the more senior participants to engage the students and the postdoc on more than just a professional level. It means a huge amount to the younger generation to get to know their mentors on more than just a professional level. So this is a long-term workshop that really gives you this opportunity to give them this extra thing that they would never normally get in a normal conference. So, and then finally, as you see, we travel all over the world. So this is where we have been so far. We travel across continents. We are trying to build a really global community of people. We are currently in the process of organizing more programs in Japan, in England, and we're always looking for ideas for other host institutions. Over the years, I suspect you will all get to see each other again at conferences and to continue to build the bonds that you've created in this program. I think you'll also get the chance to meet former alums of previous programs, and the shared experience you've had, even though you haven't met yet, the experience you've had and shared of being fellows of this program, I think will give you something to capitalize on, to get to meet them and things to relate to one another, both personally and professionally, for the years to come. So in a few moments, Rachel and Greg are going to tell you more about this particular program, the astrophysics of galaxy formation at the Flatiron Institute Center for Computational Astrophysics, and they will tell you more about the Simons Foundation. So in the meantime, I just want to thank the Kavli Foundation and the Simons Foundation for sponsoring the program. And finally, on behalf of the Executive Committee and the Steering Committee of the Kavli Summer Program in Astrophysics, I want to welcome you to New York. And I hope that this program is everything you want it to be, and a lot more than that, too.
Thank you very much, Pascal. Actually, and I just wanted to say a huge thank you. As Rachel and I, as we were trying to put this program together, we couldn't have done it without your expert guidance. You not only told us what we should do, but you correctly predicted the mistakes that we would try and make. So we're actually, Perfect. I'm very happy actually to introduce David Spergel, who is the director of the Center for Computational Astrophysics, and he'll tell you a little bit about the foundation.
Great. So I want to welcome you all to New York, welcome you to the Simons Foundation, and to the Flatiron Institute. See, do we have two slides I should pull up?
Just one.
There we go. So first, a little bit about the Simons Foundation. The Simons Foundation was founded by Jim and Marilyn Simons. For those of you who studied some mathematics, Jim's name may be familiar. It's the Simons of Chern-Simons number. So he did important work in topology, then went on to found a successful hedge fund, and then about a number of years ago signed the Giving Pledge, and they put the families put more than half their wealth into the foundation. The goal of the foundation is to support basic research in mathematics and science, and research in autism. So the foundation is based here. So the foundation offices are primarily in this building, and the foundation has a number of separate programs. One is Math for America, and are we going to use MFA facilities at all? No. Yeah, so Math for America is located a block away. It's a program that involves about 1,000 high school math and physics teachers in New York City. It runs research in autism, and there's a number of programs like there. It runs Quantum Magazine, which some of you may be familiar with, and it sponsors a program of grants in science and mathematics. You may get to meet Jim and Marilyn because they come into work in this building every day. So they may wander down and catch some of the talks and introduce themselves. If you see anyone smoking a cigarette, which is illegal in New York, that's Jim Simons. Let him smoke. About 2 years ago, Jim decided that it would be an interesting opportunity to, well, step back a little bit, give you the history. Jim and Marilyn convened a group of scientists about 5 years ago to look for new directions for the foundation. And at this meeting, Ingrid Dabouchet, who's an applied mathematician, if you've heard of her work on wavelets, suggested to Jim that he set up an institute in computational science. That there was really not an institute focused in that area. Jim liked the idea, started by setting up a Center for Computational Biology, which was based here. Then the foundation leased the building across the street, and starting 3 years ago, we started to revamp the building. Hopefully construction will finish just about the time the summer school ends. So you'll see most of the buildings is already open, but there's some parts that will probably open up just about around the last week or so. The Flatiron Institute has grown. Now, after Romeel is here. I'll stop talking now.
Thanks for warming up the crowd, dude.
So after we set up the Computational Biology Center, we added the Center for Computational Astrophysics. I came here just about 2 years ago to start the Center for Computational Astrophysics. We've grown. We'll have 6 research groups by the fall, have about 55 research scientists. We've added 2 other centers, the Center for Quantum Materials, which opened in September, and our newest center is the Center for Computational Mathematics that was just announced last week and will be led by Leslie Greengarden. And the Center for Computational Mathematics hasn't opened yet. Hence, we have the 3rd and 4th floor of the building, which was empty, which we have decided to take over and will be where you'll be staying and have your offices during the coming months. So before I turn this over to Greg and Rachel, I want to thank first Pascal, who has established a really terrific series of programs. I've heard superb things about some of the previous schools from students and postdocs who've attended. I hope that this school is as successful as some of the previous schools. And thank Greg and Rachel, who have done a terrific job putting together what will be an exciting program. And most of all, welcome all of you to the Flatiron Institute and to New York. And I hope you enjoy both in your stay here.
Thanks, David. All right. Can we get the next slide? So we wanted just to give you a brief introduction to the program. So over the next 6 weeks, there'll be the idea is to start off with a week of lectures. So this first week is we have a series of lectures on galaxy formation, including people expert in the interstellar medium, in computational methods, in the interaction between galaxies and black holes, and also the overall connection to cosmology as well. So that will be the morning. Each morning there'll be a series of 2 lectures. And then in the afternoon, the other long-term participants, so we have another, besides the lectures, we have about another 25 senior participants who will be mentors in this program, who will give short 15-minute talks on their work, so you get to meet them. And then in weeks, so in that first week is open to the public. So there are some people here who are not part of the Kavli program. You're more than welcome to stay for all of the lectures and talks in the morning and the afternoon. And then in weeks 2 through 6, there'll be a lot of research going on as the students settle into their research projects and start working. And also we'll have a series of talks given, slightly longer talks given by the long-term participants to talk a bit more about their research. So this morning we have, we're very happy to have Romeel Deve with us, and also Eve Ostreicher, who will give talks on the cosmological framework and the interstellar medium, respectively. So then, I think that's all I wanted to say. Is there anything else you wanted to add on the? Okay. So then, if you can go to the next slide, I just wanted to flash up the student participants. So these are a list of the Kavli students who will be working here over the next 6 weeks or so on various projects. And then we also have, if we can go to the next slide, the long-term senior participants. So these include the lecturers, but also postdoctoral researchers, faculty from institutions around the world. So we're very happy to have this group with us. And then next slide. The last thing I wanted to say was that we wanted to instill in this program not just a thirst for knowledge and research, but also we wanted to encourage a welcoming and an inclusive environment. So just wanted to throw up a few guidelines during our discussion here. So in particular, we wanted to encourage everybody to be inclusive, to allow discussion from various voices, to be respectful, so please don't interrupt during questions, and finally also be collegial. So we encourage hard questions, but make them constructive and friendly. And with that, I'd like to introduce our very first lecturer. So why don't you plug in and see if you can get this to work. So Romeel Dave needs no introduction, but let me give a brief introduction anyway while he sets up. So Romeel got his PhD at the University of Santa Cruz, actually, and since then he has been a Lyman Spitzer Fellow at Princeton, a Hubble Fellow at University of Arizona, and then a faculty member at the University of Arizona, and then went on to become a research chair at Cape Town University, and has just very recently taken up a faculty position at Edinburgh, University of Edinburgh. And in fact, I think that's where he flew in from today, this morning. But he is also, I should also say, he's a real expert in the use of computational methods to connect galaxy formation to cosmology. So we've asked him to give sort of an opening talk, which lays out some of the basic questions and issues that that we want to face, that we want to deal with during this conference, but also we're going to give him, so we've asked him to give the very first lecture of the sequence, but we've also asked him to give it the very last. So he's going to bring everything together at the end and tell us what we know and what we don't know. And with that, here's Romeel.
Excellent. Well, welcome everyone. So yeah, thanks for inviting me to this lovely summer school. I think it's going to be really interesting and exciting. And so yeah, as Greg mentioned, I'm going to sort of start off with an overview of some of what I think are the interesting aspects of galaxy formation. A lot of it is going to be a little bit of a review of the basic framework. First, I'm going to start with a little more observationally oriented stuff, since I'm such an expert on that, and then move on to a little bit more computationally oriented things. So, but basically, this is aimed at the students here. Okay, so this is for you guys, not so much for all the senior people who are going to kibitz and tell me how I'm doing everything wrong, and saying wrong things, but please feel free to do that as well. But I want you guys to ask questions. I really like this to be much more of a discussion than me lecturing for some ungodly amount of time, like an hour and a half or something. Okay, that's not going to be so much fun for any of us. So please interrupt me and we can discuss stuff. I have a ton of slides, but I don't feel the need to go through all of them. Okay. Okay, great. So I guess I have to use this. Maybe. Or not, okay? That was the one you gave me. Okay, now my thing is totally frozen here. Let's see what happened. I might have to. Click it out again. Yeah, I don't know what's going on. Something is jammed up. I don't particularly need to use the clicker if it's going to be a problem. All right, let's see. Oh yeah, okay, cool, great. I think we're fine. Okay, cool. Right. So yeah, brief outline of what I'm gonna talk about. Just very briefly introducing the problem. I think we're all sort of aware of what galaxy evolution is, but just so we're on the same page of the various things that go into the formation and evolution of galaxies. Talk a little bit about the various components of galaxies and how we go about observing them, and what are some of the key things that we as modelers have to think about, connecting our models to the observations, and what is going to be the key aspects of that. Then sort of get into a little bit of the meat of it, the modern way of looking at galaxy formation, which I'll try to argue is a little bit changed over what you might have learned in a similar school 20 years ago, or maybe even 10 years ago, maybe, and then focus on a couple of specific areas that I think are particularly interesting. One is the role of black holes in galaxy evolution and what we can understand about AGN, and also the circumgalactic medium. which I think is one of the most exciting new aspects and one of the frontiers of this sort of galaxy evolution studies, both observationally and theoretically, in the coming years. Okay, so yeah, as I said, please ask questions. All right, so galaxy formation, right? It's basically an initial condition problem. Okay, this is our initial condition, right? And people argue about the exact cosmological parameters and stuff, but as galaxy formation people, we don't care, right? I mean, it's basically, you know, the uncertainties now in cosmological parameters are such that galaxy formation uncertainties far, far outweigh that. Okay, so that's our initial conditions. We know that. This is the final state, right? When we go out and observe something like with Hubble, and we see all these little blobby things, they're highly nonlinear and they're very diverse. So that's the whole problem of getting from A to B. That's galaxy formation. And as you probably know, it involves a wide range of physical processes, right? So we have to think about cosmology, but you know, essentially in terms of the growth of structure and how that might lead to the correlations in galaxies that we see across large-scale structure. But then we get into sort of all the microphysical stuff, which is really where a lot of the interesting aspects of galaxy formation lie. Obviously, galaxies are made of stars, so we have to know how stars form, we have to know how they evolve, what the evolution, the end products of those evolution, like supernovae, end up doing to the surrounding gas. Chemical enrichment, the nature of dark matter might be something that could play a role, although I'm not going to talk about that too much. And then black hole feedback, as well as feedback from star formation. So essentially, you know, as a galaxy formation theorist, you know, as you students move up in the world, what you're going to have to do is really be kind of, you know, a dilettantish about astronomy knowledge, right? You're really going to have to learn a lot about a lot of different things. I mean, I never thought I'd have to know anything about thermally pulsating AGB stars, okay? I mean, what the heck, right? I'm someone who writes code, right? So that's the kind of thing that you know, pay attention, right? Learn about all the stuff that's going on, because you just never know. You'd be surprised how often it's going to be useful. So, you know, we're going to basically try to combine all these elements, and the reason for that, of course, is galaxy formation sits as sort of a nexus, a crossroads of many different areas of study. Right? And I put these arrows in both directions specifically because our understanding of galaxy formation then feeds back on something like cosmology, right? If you want to do precision cosmology, you have to deal with the uncertainties in your galaxy formation to learn more about cosmology, and so on and so forth, right? So, so this is really a two-way street, and it's why galaxy formation is really one of the most active and biggest areas in astronomy today. Okay, so that was basically the introduction. So, well, this is sort of still a little bit of the introduction. I think you know, to sort of introduce talking about galaxy formation, we kind of have to go back to the 1920s, to the old Hubble sequence, right? And we still talk about this. Why do we still talk about this? I mean, isn't this like, you know, 90 years old now? Who cares, right? Well, who cares whether galaxies are shaped differently? Well, it turns out the reason this is interesting is because the morphology of these galaxies, whether they're spirals or ellipticals or what shape they are, you know, how tight the spirals are wound, not so much the barred stuff that turned out to be less fundamental, but just going left and right on the Hubble sequence there correlates with a huge number of other aspects of galaxies. And this is what makes galaxy formation kind of interesting, that, you know, as again, probably most of you are aware, you know, the ellipticals tend to be red and dead. There's this red sequence that's sort of distinct from this so-called blue cloud of star-forming galaxies. So you have the passive galaxies up here. You have a lack of galaxies in this green valley area. And then, you know, the big galaxies tend to be at the massive end. So we think because things grow hierarchically, that means that things are moving from the blue cloud onto the red sequence somehow. The red sequence galaxies, or the elliptic early type galaxies, tend to live in dense regions. They're more clustered, and there's a lot of X-ray gas around those galaxies. Whereas if you look at the blue ones, there's very little X-ray gas, surprisingly little X-ray gas actually in many cases, and they tend to live in more poor group or field type environments. So, and then, you know, you have other things like dust. I won't go into all the things, you know, and these tend to have fairly large black holes. Whereas these, you know, can have a range of black hole masses, but tend to be relatively more modest. So it's basically this that we as galaxy formation modelers have to understand where this all comes from, right? We want to know, like if we see a spiral galaxy of a certain mass at a certain redshift, what was its typical history? What was its particular history, right? These things are all sorts of things that we want to be able to understand where things came from individually. Obviously, our Milky Way is a case example that's particularly of interest to us, but in general, we want to know both how the population evolves as well as how individual galaxies can come to look the way they do. Okay, so how do we go about observing it? Well, we have the light. That's all we have, really. So we try to, until, gravity waves start to really, tell us stuff. So we have the light. So here's an example SED from galaxies, from a particular galaxy. This is M82. You're probably familiar with a nearby starburst galaxy. So what I just wanted to highlight is, all the various aspects that we have to consider when we're modeling galaxies. And we have to think about what is the emission in each of these sort of bands, wavelengths, what is it coming from, how much is there, and what is it doing, right? So, so for instance, for this particular galaxy, well, for any galaxy really, you have the young stars, the OB stars, the things that go supernovae, the things that distribute the chemical elements around, so on and so forth. Those are of course very blue, very hot young stars. Typically, you don't see that blue light because most of it is absorbed by dust and radiated back out here, right? But in many different ways. So you can have, dust essentially reprocess light in the H2 regions, in the photodissociation regions, so on and so forth. This is the orange is from the old stars, right? So basically, once you get above maybe something like, 0.8 microns or something like that, typically, or 1 micron, you start to be dominated by the old stars rather than by the OB stars, right? So that's why basically if we want to talk about things with stellar mass, we try to look at wavelengths, rest frame wavelengths greater than about a micron. Whereas if we want to talk about young stars, we have to look over here and then hope for the best with the extinction. Then you can get, of course, these dust bumps, and so anybody can tell me what these features are? Students only. PAHs, right? Okay, so these are the polycyclic aromatic hydrocarbon features, right? No one quite knows where they come from, but there they are. So we have to, think about them, and in fact, they're quite bright. So this is important. They can be destroyed also by very hard ionizing photons. So then this is the thermal dust peak, of course, and in the case of this starburst galaxy, it peaks at around 80 microns. Typically, more in the Milky Way, it's more like 100 microns, something like that. That's basically just a superposition of black bodies from the various dust components in the galaxy. And then, way out here, you sort of have this down here, and what does the synchrotron come from? Anyone? In a star-forming galaxy? No? Synchrotron comes from basically shocks from the supernovae. So you have supernovae that go off, right? And it hits the interstellar medium, and that creates essentially synchrotron radiation. So this is, of course, very unimportant in this galaxy, but it can be very important for other situations. So that's basically the SED, and the point is that this SED varies with galaxy type, right? So this is the observational information that we can get, for at least that we have access to, both in terms of the broad bands here as well as, in some cases, emission lines. And the point is, like something like an elliptical, like NGC 5018, is not going to have a lot of thermal emission because there isn't a lot of dust. Present-day disks also don't have that much thermal emission because actually the star-forming regions don't tend to be all that obscured, unlike at starburst or at high redshift galaxies tend to look more like this, right? Where basically you get star formation a lot more embedded in the extincted regions, so you end up with a much stronger dust peak, and of course that goes up into the ULIRG regime, which are the brightest infrared galaxies. So this is the information we have from starlight, okay? And what we have to think about now, again, when we're doing our modeling, is which of our galaxy components are going to give rise to which of these peaks, and are we getting it right? and are we getting the physics of each of these components correct? So that's the stars, but galaxies are made up of other things as well, right? They're made up of gas, right? So for gas, the star-forming gas is typically, if you have, you need molecular gas to form stars, at least that's the conventional wisdom. So, so this molecular gas is, of course, a molecular hydrogen in the most, since hydrogen is the most common element, but hydrogen is very difficult to detect, so we try to use tracers. This is where things get very complicated, right? So we want to be able to measure the amount of molecular gas so we can say how efficient is star formation, right? We can measure the star formation occurring in the optical, let's say in the UV continuum or in one of the emission lines, but the question is how much molecular gas is it coming from? And that, for something like the Milky Way, we kind of have a good idea what it is, but that good idea deteriorates relatively quickly when we start to move away from things that are Milky Way-like. So, for instance, you have CO lines. Okay, so carbon monoxide is the brightest molecular tracer of molecular hydrogen. So what people typically do is try to measure CO lines, and of course CO lines are things like have different rotational quantum numbers, so 2 to 1, 3 to 2, et cetera. Of course delta J1 since you're emitting a photon, it's spin 1. And so so basically depending on the physical conditions of the galaxy, you can excite these rotational modes in the CO molecule to different levels, right? And because of that, you can get different shapes for what's called a CO ladder, right? So a priori, if you just measure one CO transition, it's not that straightforward to necessarily go back and get a full gas mass out of that. What we'd like to do is measure the total gas mass in all the CO transitions, put together some sort of a model, a PDR model or something like that, that then tells you, okay, this is the total number of CO molecules that are giving rise to all that. But it's hard to measure all these things, on top of which there's a lot of other uncertainties, okay? So not only is the density, the physical conditions an uncertain thing, there's also the metallicity. I mean, obviously, if the metallicity were 0, then H2 wouldn't trace, CO wouldn't be traced at all, right? There'd be no CO. So, so clearly at low metallicity, any sort of proportional relationship between H2 and CO is going to break down. But where and how, right? Another issue is that these molecules tend to get formed on dust grains, and so you have to form dust in order to form the molecules, efficiency, so on and so forth. So that's another complication, is the metallicity. And finally, you have the radiation field. So one of the things is that CO traces H2, but it's not a perfect tracer, right? It's not that exactly the same physical conditions that give rise to H2 also give rise to CO, right? That's not the case. So there are differences, and those differences do depend on what exactly the density, temperature structure, and the ionization structure of that gas is. And so you have to know something about your local interstellar radiation field in the regions where the CO is coming from, and this can be very difficult. This can be really tricky because essentially that's propagation of photons through this clumpy, very complicated interstellar medium. So all of these things basically, argue for really being able to understand the interstellar medium at a very high level, right? In order to be able to interpret these sort of diagnostics in a proper way. There are other things besides CO, right? So these are less bright, and so they're harder to see particularly far away. But now with ALMA, this is starting to become accessible. So here are some of the other transitions that people popularly see, things like HCO+, HCN, and so on and so forth. The thing to remember about these is that each of these has a particular critical density associated with it. So for instance, if you're looking at HCN 2 to 1, and you see a bunch of it, right? You're looking at gas that's very dense, that has density, of a million atoms per cubic centimeter, right? In typical conditions. So this is for a particular metallicity, et cetera. So, so that's, whereas something like, CO tends to live a little bit down here, particularly CO 1 to 0 tends to live down here. So this is part of the reason why these lines are fainter, is because there's just less gas living at those very high densities, right? So in principle, the idea is if we can get measurements of all these various lines, various CO ladder lines, various of these lines, we can really map out the PDF, the density distribution within the interstellar medium. And that's, I think, a very powerful way to not only understand how stars form and things, but also to help us with our galaxy formation models to understand how the interstellar medium works. Okay, so that's the molecular gas. That's, of course, not the only kind of gas, right? You have other types of gas. You have the ionized gas as well. So you can trace that in, for instance, Balmer lines like H-alpha. This is, of course, coming from OB radiation that is ionizing their nebula. So these are nebular emission lines. And those, of course, as you might guess, might trace where the star formation actually is. So those two maps are fairly similar. You can measure the amount of ionized gas pretty straightforwardly. So unlike this, you don't have too many issues. You do have to worry a little bit about extinction, but you can typically correct for that. The other aspect, the other phase of gas that's kind of not accounted for here is the neutral gas. And there is a lot of neutral gas in these galaxies, particularly as you get to low mass galaxies. The vast majority of the gas is actually neutral. Now here, actually, the challenge is more technological than observational, right? In the sense of the 21 centimeter line, of course, is a hyperfine structure, hyperfine transition of the hydrogen atom is very optically thin. It's very simple to interpret. So it really is just basically proportional to the number of H1 atoms. So that's easy. That's the easy part. The hard part is that it's really faint, right? It's a forbidden transition. And so it gets really hard to observe it, just technically challenging to observe it out to large distances, particularly at high resolution, because 21 centimeter is a very long wavelength, of course, and that means your lambda over d is fairly large. And so if you want to be able to do things like resolved maps, that becomes much more challenging in something like in something like 21 centimeter. Nonetheless, I think this is a really exciting frontier, particularly because of all the new telescopes that are coming online, the SK and its precursors, as well as perhaps some kind of successor to the VLA. So, so I think this is going to really open up a new window, and particularly, I think there's what's particularly interesting about H1 to me is if you look at H1 and start to go out, right? So you can start to probe out in, let's say, optical or ultraviolet, and quickly you run out of optical light. Okay, there are just no stars out there once you get too far out of galaxy. Interestingly, in UV, sometimes, I don't know how much you can see it, but you can see a little bit of star formation occurring in the outskirts. There are these particular examples, these XUV disks, extreme UV disks, so on and so forth. So there is some star formation out there, presumably star formation, but it's still very hard to trace. Here's an H1 map, right? And you see this H1 just continues all the way out to, you can get H1 sizes of galaxies, extensive galaxies, easy to 80, 100 kiloparsecs, okay, if you look deep enough. So that's pretty remarkable, I think, because now we're no longer talking about gas that's in the galaxy, right? We're talking about gas that's really in the circumgalactic medium. It just happens to be neutral, and typically, at least the kinematics of the few that have been examined, tend to show that they tend to be sort of rotating in the same direction as the galaxy. So it's clearly a signature, well, not clearly, but potentially a signature of accretion. And one of the things that we'd really like to know, of course, about galaxy formation is how galaxies get their gas. This might be one of our most direct probes that we have of being able to image that process and understand how this reservoir comes about and where it came from, right? So that's, I think, what makes H1 particularly interesting. Then there's dust, okay? We talked about this a little bit. I'm just going to show this a slightly different slide here. This comes from a particular model, but just to show where all the various transitions are that people typically look at. Here's the CO transitions out here in the millimeter regime, and then you have some transitions in sort of the sub-millimeter or far infrared regime, really. And the various instruments that can trace that sort of thing. If you look at the morphology of the dust, right, that's another interesting thing. So here's a map of M33 in CO 2:1 versus the dust emission. And what you see is that there is some correlation there, but it's very fuzzy, right? The dust is clearly spread out more. And one of the things this tells you is that the dust is essentially something that's tracing star formation, that has to kind of trace star formation over a longer time scale than something like CO or something like some of the other like H alpha or something like this. So so I think it's interesting to sort of look at these maps and try to understand where these features come from. So okay, finally, galaxies have black holes, right? And so we have to also figure out where the black holes come from and what they're doing, right? The first thing, step one in that, is to figure out which galaxies have actual active black holes that might be doing something. And that's already a very difficult problem. And there's a number of different ways that people try to go about doing that. So one of the ways is using these sort of optical line diagnostics, the so-called BPT diagram. And essentially the idea, again, the physics idea here, is that as you move up in this direction, you're going to harder ionizing radiation. Okay, that's essentially, these sort of line ratios measure the hardness of the ionizing radiation that the gas is seeing. And so if much of the emission is coming from very hard radiation, you expect that there's some sort of an AGN in there, right? And so that's why essentially this blue stuff, these are Seyfert galaxies, so AGN. And then there's different ways to divide the star-forming population from the AGN population in such a diagram. This is sort of more of an empirical thing to really only select star-forming galaxies, whereas this is a more theoretical one from Lisa Cooley that basically tries to be more conservative on the AGN side. And then there are these liner things, which are a big mess, very, very confusing. So these are typically things that occur in massive elliptical galaxies that essentially are not forming a whole lot of stars, but stellar evolution processes themselves at late times can give rise to some hard ionizing radiation, and this can excite the gas up into this regime as well. So, so essentially, this is one way. So you have the when people say optical AGN identification, what they're typically talking about is some sort of a line diagnostic, and there are various variants on this one. Sort of the more traditional way of trying to identify AGN is either in the X-ray or the radio. And again, if you look at an SED, and look at something like a radio galaxy, this is a redshift, I think around 2 radio galaxy. You see that, okay, you have your optical stuff and your infrared stuff, but then you have, compared to, if you remember, the previous synchrotron emission was quite low for the star-forming galaxy. Here we start to get some quite strong synchrotron emission, and what that's actually coming from is not the galaxy itself, but oftentimes these radio lobes. Okay, so you see these galaxies blowing out these big radio lobes, and that then creates the shocks which lead to the synchrotron radiation, which accelerate the particles. Or you have X-rays, right? So that's another thing. Black holes are very obviously very energetic objects, and so they can, in their accretion disk, they can create very energetic photons. So, the problem is, of course, that the X-rays can be absorbed. The radio emission is quite good, but it's not really coming from the accretion disk itself. The optical emission is good, but it's, it can be very confused. There's a big region where there's some AGN contribution, but some of it is star formation. Another thing to point out is that, as you get radio fluxes at 1.4 gigahertz above about 100 microjanskis, you're basically going into the regime of AGN. Below that, you get enough synchrotron that typically you're actually picking up star-forming galaxies. Okay, and so that's a regime that hasn't been probed yet, but will be probed quite a lot with future radio telescopes. And so I think this is kind of an interesting frontier, even from that point of view. Besides the H1 in the radio, you also have the radio continuum from star formation and galaxies at low fluxes, low radio fluxes, and that can actually provide another sort of dust-free measure of the star formation rate. Okay, so yeah.
In radio quiet AGN, do you still see that prominent?
No, you don't. Yeah. So only about 10%, people argue about that number, of the AGN are radio loud. So there's actually a fairly small minority of them. So the jets don't always look this prominent. So they're different, for the last like 30 years before they ever talked to galaxy formation people, the AGN people were just busy creating this incredible taxonomy, like, some like Carolus Linnaeus or something, of all these various AGN things that, different types and type 1s and type 2s and type 1 whatevers. So, then there was this attempt at this unification model. I don't want to talk about it because it's like a whole nother can of worms, and I'm not sure it's totally right even. But, it rapidly, there are many variations, and I think one of the things we do have to understand as galaxy formation modelers is what triggers this sort of AGN activity, right? What creates suddenly a radio loud AGN? Not all the time. Yeah?
How do you separate the H1 emission from the synchrotron?
So, well, the H1 is a line emission, right? So essentially, it will be an actual line feature. Of course, so that feature. So in a typical radio telescope, you get a data cube, right? And it's basically frequency to spatial dimensions, and that contains all the information. It contains continuum, contains the line, and so on and so forth. So then you have to go through and look for the lines, right? The H1 is another big benefit of H1 is as soon as you see H1, you know exactly the redshift, right? So that's really good. So H1 is fantastic in a lot of ways if it weren't so doggone faint, right? If we could just build take over half the moon and just carve it out and make a telescope, we'd be golden. Yeah.
So does that mean that radio quiet AGN don't have those jets, radio lobes?
As far as I'm aware, that's generally true. I don't know of too many. I can't think of any examples of radio quiet AGN that actually have jets. They may have relic sort of features out there, but active jets, no. Yeah. Yeah. I'm back.
So if you have like a massive black hole binary, can you still also get these jets?
Oh, any black hole accretion disk people here? That I don't know. So.
There's a handful of systems that people talk about with jets that show all kinds of structure, that spiral out,
Yes.
that are interpreted as a product of that.
Okay.
Point of view. From a theoretical point of view, as long as you have an inner disk, you should be able to get a jet. And so if the binary is interacting far enough separated that both have inner disks, yeah. Certainly there are multiple jets coming out of stellar systems.
Ah, right.
So, it's actually an interesting question, why we see so few quadruple jets. Like
So.
well, because if you look at the evolution of galaxies merge, when the merger takes place, you should have systems with two-jet systems, and quadruple jets are rare.
Yeah.
But it's only 10% that have these jets.
Right. So the question is, do both of them accrete?
Right, but if 10% have the jets, but we have a lot of mergers. Like most galaxies go through mergers, and quadruple jets are distinctive, right? So you can go through.
Section for merger than two single black holes because the binary radius will be the cross section for merger, so they won't stick around very long.
Well, no, I think he's talking about when during the merger process.
When
right?
there is gas, there has to be gas
That's,
around
I think, the
all
key.
4 black holes, and yet they have to be far enough
Right.
away from the center that they haven't merged.
Right. So the idea is, because I think David's point is that, the mergers of galaxies are very gaseous processes, and therefore the gas can be very quickly funneled in to the middle, and all gets smushed up and viscously, whatever, turned into a, blob. Yes, smushed up. Viscously smushed up, though. But the black holes, right, are these giant bowling balls, right? And so they should take a much longer time to merge in principle, right? And so I think my understanding of the explanation of that is that basically one of the objects, the tidal forces are such that they strip off the gas sufficiently that that second black hole is just never very active at a sufficient rate. But I don't know if that's true or not. It's just
the number of quasar pairs is
it's very small, right? I mean, we can see that. So empirically, that seems to be true. The only question is whether that is the correct explanation. Yeah, I think that's a very interesting question. Okay, any other questions on the observational sort of part? I was going to move on now. Okay, so, right. So our job as modelers, explain that, can your God do this, right? This sort of thing. So what is basically, I'm just going to sort of put it out there, because I think there's been a lot of work that's gone into understanding galaxy evolution over the last certainly 30 years. And I think one of the big impacts that simulations, and particularly gas dynamical simulations, have had is an understanding of how galaxies join up to the surrounding circumgalactic medium out into the intergalactic medium as well. And understanding this whole galaxy formation process is sort of an ecosystem rather than kind of this model of, okay, now I have a halo and I'm going to form a little galaxy in it and I'm not going to care about anything else until something smashes into me, right? So I think the paradigm that's kind of developed is one where the first thing you have to do to form a galaxy is, of course, get gas into it. And in order to get gas into it, luckily, the galaxies live in overdense knots, and you have gravity, and so you can pull this stuff in. And I think it's been shown in many simulations. Certainly, Avishai Dekel, Dushan Karish have been some of the pioneers in this, in showing that the typical mode for these sorts of accretion is quite filamentary, right? And the reason is that in order to get down into here, the gas has to cool, radiate away its potential energy, and in order to do that, of course, cooling being an n-squared process means that if you have an overdense region, you're going to enhance the cooling in that region, and it's a runaway process, right? And so you can form these filamentary structures, even though if you look at the dark matter filaments associated with it, they're not nearly as tight. They kind of look a lot fuzzier, right? But because of the way the radiative cooling interplays with that, you end up with these very tight amounts of gas coming in on these in these filamentary structures. So this is a very generic process. It allows you to penetrate through this virial radius, sort of like it isn't even there. Okay. So one of the pet peeve statements I always make, or whatever soapbox statements I always make, is that the virial radius is a completely meaningless quantity for star-forming galaxies, and it's mostly meaningless for massive galaxies as well. But for star-forming galaxies, really nothing happens interesting at the virial radius. So gas passes right through it. There's no shock there. Essentially what's going on is that the cooling rate at any given point is such that it is faster than the compressional or shock heating rate for the gas having to be funneled in. Okay, so that's essentially the condition, and you can work it out analytically for when that tends to be true. When you work it out analytically for when it tends to be true, remarkably, the number you get it's true in halo masses below right around 10 to the 12 solar masses, and that's a nice convenient number which seems to jive with a lot of other things. Okay, so that's one thing. So we can get gas sort of into the ISM mostly, but then we have to make it into stars, and that turns out to be very inefficient. And that's not entirely obvious why, right? Of course, this is a whole other field, star formation. But you can illustrate it in this sort of cosmic star formation efficiency plot, if you like to call it that, or conversion efficiency plot, where you have your stellar mass, the fraction of the baryons in a halo of a given mass that have been converted into stars. So, you know, if essentially all the baryons were converted into stars, they would all light up here. And that's what you would expect generically if you just took a halo, said, okay, I'm going to have a big ball of baryons, and I'm just going to let it go, okay, since redshift 20 or whatever it is, what you want. You will get values up here, all right? So believe me, those were the first simulations I did. I was like, my galaxies don't look anything like real galaxies. Yeah, that's very wrong, right? These points are just from Ben Moster's little semi-empirical model. But the point is, like, there's even at the peak efficiency, it's sort of maybe 20%. So only 20% of the stars have been converted into gas, and then to either side, it's quite a bit lower. So that tells you that there's feedback going on, right? That galaxies are self-regulating, that they don't just, you know, take what they have and use it up. They somehow retard their own process, or something retards it. And at low masses, and the fact that this is sort of this has two different, strongly different dependencies, argues for two different mechanisms. And no one has really been able to figure out a single mechanism that can do both of these things, right, at once. So the current paradigm is that basically below L star, 10 to the 12 solar mass halo-ish, you're mostly dominated by galactic outflows from the star-forming galaxies powered by young stars, supernovae, et cetera, and that's what regulates the mass and metal growth. And the other sort of interesting aspect that I think has become quite a bit prominent in recent discussions is the idea of wind recycling, and the idea that stuff that comes out of galaxies doesn't stay out, can come back in. And at least in some simulations, like ones we did a few years ago, that is actually the dominant accretion path for gas into galaxies at late times, for something like the Milky Way. So it's not stuff that's coming in just fresh from the IGM at all. Then, of course, you have the massive galaxy end, right? And that's you know, these black holes either growing along with the galaxies. I'll show you some data on that in a minute. And then AGN feedback is sort of responsible for this. And why do we think it's AGN feedback? Well, it's basically, you know, the old Sherlock Holmes thing. When you've eliminated all the you know, things that are improbable, then whatever's left is, or impossible, then whatever's left is right. And so there's no other energy source really in these galaxies. I mean, the type 1a supernovae are pretty meager. So the only place you can get energy to do something to suppress star formation here is from this. And luckily, there's a lot of energy in that black hole if you can just get it out of it. So I think that's kind of the basic scenario. And just for terminology, generally this part of the equation, you know, that's operating below here is referred to as the baryon cycle, these inflows and outflows and recycling. And then this part is referred to as quenching, okay? So that's when we talk about baryon cycle and quenching, that's kind of what we're referring to. So, you know, no simulation talk would be, well, no modeling talk would be complete without a movie. So here's a fire simulation just to give you an illustration of what this looked like. This turns out to be a disk somewhat smaller, a little bit smaller than the Milky Way. So this set of simulations, you probably know about fire, includes, you know, all kinds of stellar feedback, both supernovae, stellar winds. You know, obviously some assumptions are made in this. It's not quite as parameter-free as maybe some of them claim, but you know, it is an interesting model because it does really produce galaxies a lot like we see. So early on, below redshift or above redshift sort of 2, you saw it was a very chaotic system, right? There's lots of merging going on, and then there's sort of a transition period, and then after redshift 1, things really quiet down a lot, right? So, you know, you get maybe a little bit of breathing from the supernovae, but there's not any huge, big events anymore like they were at early times. Ooh, that's a nice little fun thing, right? So, you know, and then you settle down into a nice disk, and this goes for a while. And the point of this, right, is to say that, you know, what are the various things that are giving rise to all this? Now you start to grow a disk, right? A nice thin disk, if you could look at it edge on. And you know, there's basically several things going on. One is, of course, the star formation rates are higher at earlier times. You know this from the Maddow plot, right? So the cosmic star formation rate and the star formation rate of individual galaxies is higher. And this causes more energetic feedback at early times. There's also more merging going on at early times because the universe is smaller and there's just more stuff around to merge with, okay? So the universe, so there's more merging. And the gas accretion rate is also lower, okay? And we'll talk about that in just a minute, but that's basically, all of these things sort of conspire to give rise to a very different behavior when you look at a galaxy at redshift 2, even if the same mass, than one at redshift 0. Okay, so that's very complicated, and that took like millions of CPU hours and all this sort of craziness, right? Can you do any sort of interesting modeling in a fraction of a CPU hour, right, that you can do in your brain? So let's talk about essentially modeling galaxies in a very, very simplistic way and see how far we can get. But I think that this is very illustrative because it sort of encapsulates a lot of the ideas and sets a good way to think about how galaxy formation works. So the way I like to think about galaxies is that galaxies are gas processing factories, okay? So you have your little factory here, right? So there's a factory, right? Okay, so what are you gonna do with a factory? Well, a factory needs raw materials, right? You're gonna make something out of this, right? So the raw materials are coming in from the intergalactic medium. And the good news is, thanks to CDM and lambda CDM or whatever, we know what this is to reasonable accuracy, not great actually, but reasonable accuracy, at least out at something like the virial radius. So we know how much material is falling in, baryonic material. The problem is, of course, it's a supply chain. There's always, somebody who has to take a bribe and something falls off the truck or whatever. And you only get some fraction of that actually coming into the galaxy, right? So let's just call that zeta for now, right? So you have this sort of zeta parameter, and that corresponds to effectively what you can think of as preventive feedback. So, what was prevented that was accreted onto the, far away, let's say at the virial radius or whatever far radius you want to pick, versus what actually made it into the reservoir of the galaxy to be eligible for star formation, right? So let's call that zeta. Okay, now you got to make a product with that. Well, obviously galaxies make stars, right? So you have a bunch of stars that get made, but it's with any galaxy you have some waste product. So you have the waste product that's going to be ejected out of it, and the ratio between the rate of formation of stars and, the ejection process versus the rate of formation of stars is typically denoted eta. This is called this mass loading factor. And so that's going to be the ratio there. But of course, we live in the 21st century, and we need environmentally friendly factories. So we have to recapture some of that waste, right? So we have this term, which basically is what fraction of, or on what time scale, if you want to think of it that way, does the material that's ejected eventually come back into the galaxy, right? So in this little very simple scenario, I can essentially write down mass balance. And if I write down mass balance, I can figure out what is this term? What is the rate of formation of the stars, right? And that turns out to be this, which is, again, just fairly straightforward to see. It's the term coming in from this, the term coming in from that, divided by 1 plus zeta, all right? Very simple. Turns out you can also do the metallicity. So if you say that if you form some stars, you have to enrich this. This is the unenriched component, right? This component came out of the galaxy, so it's already enriched, so you don't need to worry about the enrichment of that. But if you enrich just this component with some metals that, every time you form some stars, you enrich with some yield Y, then that's the metallicity as well. Okay, so these are our parameters, right? There's zeta, there's eta, which is ejective feedback, so preventive feedback, ejective feedback, and something to do with wind recycling, however we want to parameterize this. Let's say, recently people have been talking about this recycling time. So I like to call these baryon cycling parameters because this is essentially what baryon cycling is doing, right? Okay, so that was a little bit glib, right? Because there was an important term that I forgot. I didn't just forget it, I actually intentionally ignored it, which is this reservoir term. So you can imagine that stuff comes in, it never makes it, it just piles up on the loading dock, right? It never makes it to actually into the factory. The interesting thing about this is, we looked into this back in 2008, and other people have looked into it as well, is that this term evolves, it's not zero, but it evolves much more slowly compared to these other terms, to the point where it's a decent approximation to neglect it, okay? So if you neglect that term, then you get these equations. You can also write down the gas fraction. This is essentially just rewriting the definition of the gas fraction. And then you can get your m dot from gravity, from the IgM, just based on CDM and some fitting functions. Okay, so you have a bunch of parameters, this is an incredibly simple model, right? Does it have any hope of working at all? Well, we thought, oh, well, why not try it, right? Just, what the heck. Let's put our 3 parameters, create a amplitude, a mass dependence, and a redshift dependence. So that's 3 parameters for each, so that's 9 total parameters, right? Throw it into a big MCMC and say, oh, let's get a bunch of data and constrain to it. Okay, what kind of data can we constrain to? Well, we can constrain to things like the stellar mass-halo mass relation, right? That's kind of a fundamental thing. So is the mass-metallicity relation if we're predicting metallicities, or this thing called the main sequence, the relation between stellar mass and star formation rate. And the answer is it's not bad. Surprisingly good, actually. So for one that has basically 9 parameters, and in fact we get it down to 8 based on some Bayesian evidence stuff, we can basically, to a decent chi-squared, reproduce these sort of, both the evolution and the amplitudes of all these models. Okay, so why is that interesting? We threw in a bunch of parameters, who cares, right? That was sort of fun, but did we learn anything from that? Well, we learned some generic things, right? Because what we can do is then say, okay, what sort of baryon cycling parameters did we need in order for us to get a model that worked, right? I won't show you the Bayesian posteriors, but they're actually fairly tightly constrained. So these things are not terribly free, right? And so there's some generic trends that you can, I wouldn't pay attention to the exact numbers here, right? This is too simple a model for that. But the generic trends turn out to be something that people who do simulations or semi-analytic models have kind of arrived to independently anyway, just by trial and error. But here we can sort of see where it comes from, at least in this very simple model. So what are some of the generic trends? Well, the first generic trend is that the mass loading factor has to drop strongly with mass, right? Has to increase to low masses. And so as you're getting down to low mass galaxies, particularly at high redshifts, you can get mass loading factors of 10s or 100. That's what we seem to need. Whether or not we can actually figure out the physics that gets that, that's a whole separate question, right? But that's what, at least in the context of this silly model, that's what we would seem to need. It's not that silly because these sorts of trends actually agree pretty well with the kind of things that you get out of, if you go measure it in the fire simulations, let's say, okay? So they're not too dissimilar than this. And they do have that same sort of trend. There's a sort of a weak redshift evolution. I think this is more controversial. It's not totally necessary. You could sort of probably get away without it. But the other thing is, of course, that we have to have strong preventive feedback at the mass of galaxies. And you can see this sort of feature that we introduce by introducing a quenching mass scale above which we no longer allow galaxies to accrete as part of our preventive feedback. And and so that again tells you that just simple star formation, one of the things you could think about is saying, well, as you get big enough halos, you will have sufficiently long cooling times that the gas just won't cool, period, right? And that's the trend you start to see here. You start to see more and more shock heating as you get above 10 to the 12 solar mass in the halo mass because the cooling rate at the virial radius is no longer fast enough like it was before, right? So you start to see that trend, but there has to be a break here. There has to be an additional thing, okay? And it's very difficult to work things without it. The other thing is to look at the recycling time, right? Just sort of get an order of magnitude ballpark estimate of what this is. This is in gigayears, right? So in gigayears, basically, has a relatively some dependence on mass, but and redshift, but basically it's of order a gigayear or so, right? And it's smaller in high mass galaxies. So high mass things tend to recycle faster. Okay. You might expect this again on physical grounds simply because high mass galaxies are more massive. They're able to hold on to their have larger potential wells. So most current galaxy formation models, again, not using this thing, but basically have arrived at similar scalings, or at least qualitatively similar scalings, from completely independent considerations, right? So that's why this model is interesting, is because it actually encapsulates these sorts of trends that we need in the baryon cycling parameters in order to get galaxy formation models to work, right? And that's I think that's one of the key lessons that we can take away and say that we now understand this part, what we need to get. The question is, of course, what is the physics that gives rise to any of that? And that's a whole separate thing. So interestingly, so far I haven't once talked about merging, right? So in this model, so there's essentially very little merging going on. You can think about the scatter associated with the fact that halos aren't, the dark matter isn't smoothly flowing in, the gas isn't smoothly flowing in, it's coming in lumps, right? And if you do that, I won't go into all of this detail here, but let me just skip over that part. But basically, you can get you can show that essentially the inflow fluctuations lead to a scatter around these sort of the scaling relations I was talking about, the stellar mass, halo mass, the mass metallicity, so on and so forth, right? And so this is the example of the scatter around the main sequence, the star formation rate stellar mass relation, directly from inflow fluctuations in this simple model versus what's actually been observed. And of course, many of these contain observational errors, so they're sort of ours should be below that. Okay, gas fractions. I just wanted to mention sort of gas fractions. What are the gas fractions doing, right? So okay, we said that the gas reservoir is slowly evolving. Can we make more quantitative predictions for this, right? Because we can now observe gas out in galaxies to fairly high redshift. And the answer is yes, but we have to invoke one more piece of information. And that is, how fast is the gas getting consumed once it comes into the reservoir? So, what's the production line speed, right? Luckily, that seems to be relatively well constrained, at least locally, that if you look at the star formation rate of let's say disk galaxies today, you convert typically maybe a couple % of your gas mass into stars within a dynamical time. Okay, that's kind of a variant of the Kennicutt-Schmidt relation. So if your dynamical time in a simple disk model, is like Momau and White or something like that, scales with the Hubble time, then this is basically the inverse of the Hubble time, which at high redshift would be something like 1 + e to the 1.5. So the gas consumption then, that's the rate at which you can consume the gas. Well, how fast is the gas getting supplied? Well, the gas getting supplied from the intergalactic medium, that inflow, if you remember that power, is something like 2 to 2.5, somewhere in that range, right? So this power is higher than this power. If that power is higher than that power, it means you go to sufficiently high redshift, you're going to be dumping gas onto that galaxy so fast, it's not going to be able to keep up, right? You can calculate what that redshift is, again, within context of some assumptions, and I won't go into exactly how this is derived, but basically you get values of around something like 4 to 6, depending on exactly the mass and so on and so forth. So once you get into the high redshift regime, you would expect that galaxies can't keep up with forming stars. If, the big assumption, this still holds, right? If it's still converting only 2% of its mass into stars in a dynamical time. If it's faster, then of course it can reach equilibrium earlier. Okay, so there's this initial gas accumulation phase, but then after that, right, you can get you can just compute what the gas fraction is based on the depletion time, which I got this scaling from simulations, but is reasonably consistent with data. And then this is the evolution of the specific star formation rate, where beta is just the power of the specific star formation rate versus stellar mass. And you end up with this type of, which typically something like minus 0.2 or something like this. So you end up with something like that. And this is about what's observed, okay? So essentially, if you look at a Milky Way galaxy today, right, your gas fraction is about 10%. At redshift 2, the power here is about 1, so at redshift 2, it should be about 30%, and that's typically what you see for something of the same size. So, so essentially, this slowly evolving gas reservoir just reflects this competition between the inflow that's dumping stuff onto the loading dock versus how fast you can take it off and form it into stars or eject it into an outflow. Mm-hmm.
Is that 1 + e supposed to be a -1?
No, that's
Tilde 1?
yeah, that's a tilde 1.
You mean more or less?
Yeah, more or less 1. So the problem is that this 1.5 only holds at high redshift. When you get to lower redshift, the lambda that makes it closer to 1 + z. And then, this is an uncertain number. Okay, so yeah, so that's basically, this sort of simple galaxy formation model. And then we're trying to understand some of the physics associated with that, right? So one of the physics that's associated with that is the fact that we have to quench these massive galaxies. And we have to figure out what it is that's actually doing that quenching. Again, by simple reductio ad absurdum arguments, we say it's the black hole. Okay, so what are the black holes doing? Well, the black holes are doing, as you know, of course, correlated with the galaxies fairly, not super strongly, but at least reasonably strongly. It appears that the black hole mass to stellar mass ratio for bulge-dominated systems is not evolving very quickly. Maybe it's evolving at higher redshifts, but there's a lot of selection effect issues, so it's not totally clear. So there's something that is basically co-growing the black holes roughly with the galaxies, averaged over a sufficiently long time scale. Okay, maybe that's not surprising. Bigger things are bigger, so if things are growing their stars, they should all also grow their gas. That's true. That could be the case. But there's also a lot of evidence that the black holes are impacting the galaxies themselves. So, for instance, we can see black hole feedback, right? So we talked about jets already, but there's a lot of work going on recently about these molecular outflows. So in a molecular outflow, what they're looking at is, again, these CO lines or something like that. They look at a line profile of something like this starburst, AGN starburst Markarian 231, and you see that it's not Gaussian down here, right? One would expect if all the molecular gas were just rotating in the disk, you would see a Gaussian profile, but you don't. You see an additional term which extends out to quite large velocities, much higher than the circular velocity of the galaxy itself. And this has been interpreted, this is commonly interpreted these days now as molecular outflows. So these are outflows that are being generated by the starburst, either the AGN or the star formation. They're extended. They actually, if you add up the kinetic energy, because you can measure the mass in this term, now that you sort of know it, and make some assumptions, of course, about how to convert CO to H2, which is very uncertain, but if it's a few hundred solar masses per year, you're talking about kinetic powers that are a few percent of the AGN, a few percent of m dot c squared. So it's very large, with large momentum rates, okay? So it's mass loading a lot of stuff as it's going out. So this, you can say, okay, this little black hole here is dumping a huge amount of energy out here, and that's gonna, slow the cooling, so on and so forth. But this is a way to actually just get rid of the gas altogether. I mean, you don't have to do this for very long, 10 million years, and you got rid of 10 to the 10 solar mass of gas, right? So that's that's potentially another feedback way of doing things. Okay, I think, I think I'll go through this very quickly, but I think it's sort of the overall picture. I think that has been coming together from various things as of maybe 5-ish or 10 years ago, is that you start out with a disk, you merge them together, you form a ULERG, then you have sort of a blowout phase, which results in a sort of a naked quasar, and then you decay into a post-starburst galaxy, which eventually ends up into a red and dead elliptical. So this is one scenario for how to quench galaxies. Right? This is sort of what you might call a rapid quenching mode associated with this blowout phase, which we might be catching as these molecular outflows, right? Is this the way all galaxies quench, right? Do all massive ellipticals go through this phase? And I think the answer is almost certainly no, certainly today, right? And the reason is very simple, actually, when you start to think in a cosmological context. So the problem is the early simulations were done sort of isolated things, and the great thing about an isolated simulation, you smash two things together, nothing else happens to it. It's totally isolated, no further infall or anything like that. It just sits there, right? So you might get the wrong idea about what's going on compared to having continual cosmological infall. And so many semi-analytic models looked into this. We sort of simply confirmed it basically with hydro simulations that if I think Darren Croton's was the first one to sort of talk about this and coin the frame radio mode at least. That if you just have this hot halo that forms for some reason at the virial temperature, and you allow that hot halo to just stay hot, somehow prevent cooling in anything, you can really get most of the properties of red sequence galaxies just fine, right? Without ever having to invoke any kind of a blowout or merger associated thing. And so that's what we confirmed. I won't go into all the details of it, but basically the punchline from our simulations was that hot gas and massive halos drives both mass and environment quenching. So what are those two quenchings we're talking about here? Well, if you plot the overdensity versus the stellar mass and populate this plot from a galaxy survey for what fraction of galaxies are red, defined in some way, right? What you find is that things that are either very dense at any mass or very massive at any density are always red, okay? So these things tend to be satellite galaxies. These things, of course, are very massive central galaxies. Both of them seem to get quenched in this sort of, and so I think one of the questions was, well, is the satellite quenching due to satellite-specific processes like tidal stripping or ram pressure stripping, et cetera, whereas this is something completely different. It turns out, at least in some hydro simulations, you can basically get it all from the idea that essentially the radio mode feedback idea that if you just keep the hot gas hot, you will produce a red population as you see. So that's sort of the counterpoint of it. There are counterpoints at the other direction. For instance, post-starburst galaxies seem to have a very short star formation quenching timescale. You can actually track the star formation history over the last several hundred years, and it seems to have truncated very quickly. Maybe you can't do that in this sort of simple, slow quenching mode. So what fraction is in this mode versus what fraction is in sort of the fast quenching mode, I think is a pretty interesting question that's still sort of open. Okay, any sort of questions on that? All right. So I wanted to just spend the last couple of minutes talking about the CGM. All right, I think this is super exciting stuff. So here's the basic idea. The problem is that we think that all this baryon cycle stuff is what's really governing galaxies and blah, blah, blah. Great, so let's go out and observe it, right? Okay, great. Let's observe some inflows and observe some outflows, right? Really hard. So we can do maybe these molecular outflows in these very bright, few rare cases. We can try to see, use the spectra of emission lines coming out, absorption lines coming out of galaxies to probe some stuff. But it's very difficult. And the idea is, the CGM is something like this, right? So you have this accreting gas that's kind of joining onto the disk. You have these outflows that are going out. Some of it is recycling. You have some component of diffuse gas out there that's sitting there. It may be hot or not. This one doesn't even show satellite galaxies, but there are probably a few satellite galaxies out there, so on and so forth. So the idea is that if we can, the problem is, of course, that all this gas is very diffuse, it's dynamic, it's not necessarily in equilibrium, might be moving around, might be out of thermal equilibrium even. So how do we probe all this? Well, if we had a sampling of flashlights that we could shine through this gas and create absorption lines, maybe we could learn something, right? And so this is basically the kind of thing that people have really tried to do. Turns out a lot of the interesting absorption lines that one looks at tend to be in the ultraviolet. So these numbers are in angstroms of their transition wavelength. And so low redshift, one has to go to space. At high redshift, one can do this from the ground. But in either case, I think this is I think a really exciting way to try to probe stuff. And just to kind of illustrate some of the ways in which this can govern galaxy formation, really you can sort of ask a lot of questions of the CGM, even from the very highest redshifts, right? So this is something that Christian Finlater has been working on with some radiative transfer galaxy formation simulations to explore very high redshifts, so epoch of reionization type things, where now, thanks to infrared spectrographs, those UV emission UV absorption lines are now redshifted into the infrared. But you can actually get absorption line measures of things like carbon-2 and carbon-4, also silicon-4. And what you can try to do is try to then say that, okay, you have these sort of background quasars, they're probing through these galaxies, they're seeing these absorption lines. What does that tell us? Like, what is the meaning of that, right? And this is where simulations can be very powerful, because in principle, if you're doing everything correctly, which of course we know we aren't, but hey, do our best, we can answer that question directly from the simulations, right? And so, so this is the kind of thing we do, is we can shoot absorption lines through these simulations and try to compare to the data and try to ask the question, what are these stars doing? So again, one of the important things about early star formation is that it puts metals into the CGM, and those metals then impact the subsequent generation stars because they're no longer metal free and they have a different IMF, et cetera, right? So, how do we go about measuring that IMF? This, the CGM might actually be one way to do that, right? Looking at line ratios of some of these things as the data gets better. Again, the photoionization from the CGM is suppressing growth in these photosensitive halos. So again, you have UV light coming out of these first galaxies, and that can actually impact the surrounding galaxies. And this may be, for instance, where Milky Way dwarf ellipticals come from, right? So, so then again connects to sort of near field cosmology type stuff. And then, also 21 centimeter emission. So as the galaxies grow, right, you now enter a regime sort of, getting close to cosmic noon, as they call it, where you see outflows all the time. So at redshift 2, Chuck Seidel has made a living out of this, of basically finding, galaxies, getting spectra, and showing that they have very blue-shifted absorption lines out to 800,000 kilometers per second at most. And these things are obviously outflows, and from these outflows, essentially one can deduce that basically every star-forming galaxy of this epoch is putting out pretty massive outflows, okay? The interesting thing comes when you want to say, okay, well, that's taking a galaxy and going right down the line of sight, but can we take a galaxy and figure out what's going on in the CGM of that galaxy? Well, that's pretty hard because there aren't that many background quasars. They don't happen to be in the right place. But you can use other galaxies, right, if the other galaxies are bright enough. At the moment, they're not really bright enough with 8 and 10 meter telescopes, so he has to stack. So this is what Chuck did in a very famous 2010 paper, is he took galaxy absorption in galaxy spectra and correlated with the foreground galaxy, and basically was able to measure, for instance, the equivalent width profile of these various ions. So again, this is directly probing some combination of metallicity, ionization conditions, and density. Those are the three things which set how much carbon is in carbon-2 versus carbon-4 or whatever, as a function of radius out to these galaxies, out to these sort of virial radii type things. I think that's something. This is, people ask me, what do you think is going to be the biggest thing from 30-meter class telescopes, right? What's going to be the most exciting science from 30-meter class telescopes? I think it's going to be this. We're not going to have to do this with stacking anymore. Okay, when we have factor of 10 more area, we just do this on a galaxy by galaxy basis, right? And that is going to be incredibly powerful, I think. So that's sort of one area that I think is quite exciting. The other thing that's happening in this epoch is, of course, the first AGN and the first quenched galaxies are appearing. And here's a real argument for why this fast quenching mode might come about, because we see red galaxies already at redshift 2.5, 3. Okay, so is there enough time for something like a slow, quiet, slow quenching to actually work? And I suspect not, right? So it may be that the nature of quenching is quite different at those epochs than it is today. We already talked about cold filaments. Yeah, we talked a little bit about settling and trying to understand, how the inflow from the CGM is actually changing as a function of time. And then we get to the present day, and I think one thing I haven't talked about much, but I think is particularly interesting, are these X-ray halos. So that's, of course, another form of CGM that's been studied for quite some time, which is X-rays, diffuse X-rays in things like galaxy groups. So this is a galaxy group, and the purple is the Chandra X-ray emission. And not a lot is happening here, but as you get really deep data, you start to see, I mean, even in this relatively modest sized group, you see these sort of bubbles out here, you see the structure, so on and so forth, right? So clearly things have been happening in this intra-group medium, right? And now one thing is could be, infalling satellites or infalling groups or something, but the other thing is it could be coming out of here. And when you see stuff like this, it sure looks like it might be some double lobe thing that's coming out of the galaxy, right? So is that the smoking gun, right, for this sort of AGN feedback that we need to quench galaxies? And can we understand the X-ray properties? We know that shock heating creates these X-rays, but if all this energy is being dumped into these galaxies from the black hole as well due to these jets, surely there's some signature there, right, in something. And can we create a model that self-consistently produces not only the overall X-ray properties just from the shock heating, but also from the additional contribution from the jets in a particular way? So I think, okay, so I'm pretty much out of time, so I'll stop. But hopefully this is kind of a little bit of a core dump. Sorry about that, but it's kind of, I think, hopefully getting you excited about all the different things that are going on and how they all connect to each other. And I think that's the real thing to sort of try to take away from, particularly from a place like this, where you're going to be for interacting with lots of people doing a lot of different things. That maybe there are connections there that you haven't thought about, and it's worth thinking about, because I think that's where some of the really interesting progress comes from, is when the black hole people stop doing taxonomy and start doing talking to the galaxy formation people, and the galaxy formation people stop treating black holes as if they're some weird thing that we don't have to care about. So these sorts of things I think really push the field forward. So that's something I would encourage you to do. Okay, so I don't have to say all this stuff again, but yeah, I think that there's many different interesting physical processes that have to be explored, and the key message I think is, while we have this sort of very broad brush, heuristic picture of how galaxy formation works, we really have essentially very little idea about what the actual physics is. Okay. And I think that's really where of course we want to go. We don't necessarily just want to have a model that creates fake galaxies. We want to understand the physics, right? So that's I think where I think that a lot of the work has been going, and particularly towards small scales, understanding both the interstellar medium as well as understanding black hole accretion processes and understanding the creation of those types of feedback and associated feedback. So that's, I think, where the field is really headed, is trying to break through some of these small scale barriers and try to work towards a deeper understanding of what is the actual origin of these of all this sort of outflows and inflows and all that. Thanks.
Thank you, Romeel. We had questions throughout, but are there other questions? Yeah, if you can push the button. Speak straight into it.
So my question is preventive feedback basically negative feedback, or is that different?
Yes, I think that is the lingo, right?
Well, I think
Positive feedback means
feedback
stimulating star formation.
negative feedback usually means that you're preventing star formation or making star formation less efficient. But I mean, there's ejective versus preventative, both of which are negative feedback.
Both are negative, right?
But ejective means you blow the gas out to prevent stars from forming, whereas preventative means you prevent the gas from coming in the first place and thereby reduce star formation. I think you invented those.
No, Neil did. Well, he invented velvet rope feedback versus bouncer feedback. So the bouncer feedback kicks you out, whereas the velvet rope feedback prevents you from getting in the club.
Well, in principle, there is also a third possibility that you have the gas, which comes in but doesn't form star because maybe it's ionized or something.
Well, that's right. So that's another type of preventive feedback, which, exactly. So preventive feedback can be in a lot of different places. There's certainly a lot of preventive feedback going on in the ISM, right? Because that's why star formation is so inefficient. So we know that happens, and we don't totally understand how that happens, and that could, as you say, be quite different under different physical conditions.
Other questions?
I shouldn't be asking questions, being
should.
not as student-oriented these days, but in this respect, I sort of am. I thought it was a great talk, by the way, very comprehensive. So we have two paths, trying to take both paths. One is the simulations as numerical experiment with various control parameters, and the other one are these sort of global laws. And the global law ideas have sort of grown with extra parameters over time. And ultimately, one hopes that there will get to be an interesting convergence of the two approaches where you've encapsulated the essence of the simulations. Part of that is to adequately deal with all of the fluctuations that occur around any sort of mean properties you might get from looking at an ensemble. So if you were forced, as I'm trying to force you to, looking downstream 5 years or so, where do you see all of that going? And do you see that we will actually have a fairly adequate model in which you could just sort of lay the results down on n-body simulations as opposed to requiring the full-up hydro?
I certainly hope so. I think, you know, I mean, I mean, the SAMs have already made a huge amount of progress towards this, but one of the things, that's a great point you brought up, Dick, because, you know, I think one of the futures of these sort of scaling relation ideas, right, is not the scaling relation themselves, but the scatter around the scaling relation. And actually, that's kind of where the interesting physics ends up being, right? So, yeah, so, you know, things like the fundamental metallicity relation, you know, that thing at a given mass, the star-forming galaxies tend to lie at lower metallicity. You know, you can have similar things for the gas fraction and so on and so forth. And again, I think that what these highlight is this idea that, you know, we call our little simple model an equilibrium model. Why do we call it that? Because galaxies like to live at an equilibrium that is on these scaling relations. So any deviation, when you kick a galaxy off, the physics conspires to put them back on, right? And that's why these scaling relations like mass metallicity are so tight, right? So if you go off from here, you accrete a bunch of low metallicity gas, you don't gain in stellar mass, but you lower in metallicity and you gain in gas content, which also boosts your star formation rate, right? So that's how something like the fundamental metallicity relation might emerge from this sort of fluctuating inflow paradigm. So I completely agree that the interesting questions now, I think, for the models, for these simple models, is to see if we can recover these, right? Because if we can recover those and really understand where those come from, now not only are we populating our n-body simulations, you know, just with the mean relations, but we're populating them in a way that encapsulates the scatter and its dependence on whatever environment, you know, immediate accretion rate, et cetera.
Can I just do a quick follow-up on that?
Mm-hmm.
The point is an excellent one. So I like this idea that there are attractors and that you are essentially going back with relative perturbations into the attractor basins. And then the issue is how many attractor minima there are, and do you kick over? I mean, it presents a really interesting forward theoretical vision for the subject if it can be proved. Do you think that that's probably going to emerge?
Well, I think Rachel is better suited
okay.
to me, right? I mean, I think the semi-analytic models are certainly getting there, right? That they can certainly predict these things in a fairly sophisticated way.
Well, I'm thinking sort of a Langevin type approach where you fluctuate around, and you sort of have this guide, which is scaling, and then you can fluctuate, but you can fluctuate over into another minimum if the fluctuations sort of build coherently enough. Is that part of the emerging picture, Rachel?
To some level, I don't know of any
Has
obvious.
Has it been formulated in any way like that?
I mean, the problem with this is that, when we look at something like the mass metallicity relation, we don't see a second branch anywhere. Right? Okay. We see a large scatter. What's that? So, sorry? So, of course, these are only star-forming galaxies, so then you would have to look at the stellar metallicities, of course, to look at the ellipticals, which do different things. That's true. The problem, maybe metallicity isn't the best example because the calibrators are somewhat uncertain. But in principle, you should be able to match up the gas metallicities and the stellar metallicities and put those on the same plot. When we do this in simulations, we can match roughly both the stellar and gas metallicities. Not great. Other simulations do better than ours. Within a single paradigm that basically says that, okay, once you quench galaxies, you just start to evolve much more like a closed box, and so you start to just climb up in metallicity. So I think that's specific to metallicity, but I think your point is much more general than that. And I think that the generic point would be that we would have to identify a separate locus that things tend to be attracted to, and I would say that that's not obvious for many of the scaling relations yet. But again, there's lots of systematics.
Just to follow up on Dick's question, I think an example of what you're talking about is we think that galaxies grow along this so-called star-forming main sequence. The whole name is sort of meant to represent that this is something fundamental. Of course, some people don't like that name, but the galaxies grow in mass and star formation. And I think one of the puzzles is whether that is driven by cosmological conditions. Is it driven by accretion rates from large scales, or is it driven by the physics of star formation on small scales? And I think that's something we're still trying to work out, is the interplay between the large scales and the small scales. That's sort of an overarching theme of actually the structure of this whole meeting that you might notice if you look at who the lecturers are. So that's not an accident. But then I think that there are processes like quenching, for example, that then clearly disconnect galaxies from that evolution along these sequences. And I think part of what's so complicated is that those sequences can be manifolds, right? So for example, we think metallicity, there may be a fundamental plane that galaxies are evolving along, and it may even be more than just 3 dimensions, right? So there are these sort of high-dimensional planes that I think galaxies evolve along and then perhaps detach from. And so understanding when they detach and why they're confined to these manifolds, I think that's the really fundamental question.
Oh, yeah. It should work.
So I was just thinking, if you think of some manifold and it has some, I think the idea is like the star-forming main sequence is the attractor. Here, you need for some attractor to happen, you need some dissipative process for it to work. What is that in this context?
Right, I think you don't necessarily need a dissipative process. What you need is a process that forgets its previous condition, in the sense of, so in the context of galaxies, you can think about, why do things evolve back towards, let's say, mass metallicity or stellar mass, gas mass fraction, and the answer is, when you sort of look, is that it evolves back on a time scale corresponding to growing by twice in its mass, right? So effectively, once it sort of forgot about its previous perturbation, right, by accreting a whole bunch more, that new accretion occurs in a way that puts it back onto the relation, and that kind of helps it go back, right? So it's the stochastic averaging, essentially. In fact, people have talked about this as an origin for the main sequence, but it's, you can explain it mathematically that way, that essentially there's an attractor solution, and basically, your stochasticity will tend to average things out, and you'll get sorry? It's a stable point, that's right. And so, but that doesn't, of course, tell you the physics, which is the more interesting aspect of it. But Yeah, so I think the dissipation here, if you want to think about it, a dissipative term, I guess, is just the continued growth of the galaxy in a way that is decoupled from its previous evolution, right? So you end up just averaging.
Okay, so I think we've gotten to a break. So let's thank Romeel again. And we'll take a half-hour break, so be back here at 11:30.